Hello, welcome to an extra lesson on the ML curriculum. So in today's lesson we'll be learning about the minimax algorithm. So please give me a lesson on the minimax algorithm. So this is unsupervised learning. Unsupervised learning as an extra lesson. Please explain the concept, then give me a code example, and please, for the final part, give me a fully functional textual based tic-tac-toe game with the minimax AI. So yeah, just as a precursor, so minimax is basically when you're trying to maximize your own score but minimizing the other player's score, and it makes tic-tac-toe like literally unbeatable with go. It says so tic-tac-toe, which you don't need any optimizers. Chess, which you do need a lot because they're like, I think it's like over 1 trillion different combinations. And Go is, I think, like, it's a game popular in Asia. I've played it once or twice, but I don't really get it. It's like, it's got loads of, I think they're called stones, and you try to enclose all of their liberties, and then you get them, just as a extra. Okay, so the minimax algorithm is used in decision making and game theory, commonly for two-player zero-sum games like tic-tac-toe, chess, and Go. In these games, one player's gain is another player's loss. The minimax algorithm assumes that both players will play optimally and try to minimize the possible loss for the worst case scenario. This is called minimax because it minimizes the maximum loss, the worst case scenario. So this is good for turn-based games, like tic-tac-toe, chess, and Go. So the basic idea behind the minimax algorithm: a maximizer tries to get the highest score possible. Minimizer tries to get the minimum score. Minimize the maximizer score. Sorry. The algorithm recursively explores all possible moves in the game and picks the one that maximizes the score for the maximizer and minimizes the score for the minimizer. This is why in chess you need those. You can't just do it recursively, as quite literally trillions of combinations. So minimax in tic-tac-toe. So the AI tries to maximize its score. The human player tries to minimize the AI score. Each move is evaluated by using a scoring function. It says 10 points here, but just one could be useful because you could have 1 win, 0 draw, and -1 loss. So 10 points for a win by the AI, minus 10 points for a loss by the AI, human win, 0 points for a draw. The algorithm goes through all possible moves, simulates the game, and chooses the move with the best possible outcome for the AI. So code example. Okay, so I'm just gonna get to the bit for the actual minimax. Okay. So what you see here, it's a recursive, so we can pass is maximizing or is minimizing to it. So if check when board is O, okay, so we're factoring the depth of it as well. Okay, so 10 minus depth, and x is depth minus 10. So if the player wins, that means that it'll be the deeper the depth and the player wins, the less loss. But if AI wins, lower the loss, and if the player wins, high loss for the AI. If it's draw, we just return 0. But we can just do -1 and 1 minus. Oh, I see why it's doing that now, because of depth. So it's positive. Okay, yeah, that makes sense. Okay, actually. Okay, so if it is maximizing, we first start the best score as minus infinity. This means that any value is greater than that. Okay, so For I in range 9, if board is equal to just the space, so there's no move there, the AI goes there, so it's O, and the score is so we're getting the score of this current state now where the AI's just moved, and then board I equals 0, best score equals max, and then okay, so we're storing the score there, return best score. Else best score, so this is if it's minimizing, we want to, it's positive infinity, we want to get a lower score. So we find out the AI's best score as being the best. So what we're going to do is we're going to loop through all the possible moves, and then we're going to find which of these moves can get the highest possible one. So that's why we're doing it here as well. Okay, so best move, and we're going to call minimax. We're going to set it to just this again after. So then we're going to do score is greater than best score equals score, return move equals I. So we're going to return the best move and then play game. Okay, let's see the AI. AI best move. So move equals 0. Okay, yeah, we're assigning move to I because that's the position in the board. Okay. So then, we're gonna get the best move for the AI, and then board AI move is going to be O, and then we're gonna print the board. So now I'm just gonna copy this and paste it into a online Python IDE. I might actually use, I know, Godbot doesn't accept input, so I'm gonna do online GDB. Okay. So I'll paste it in here. Okay, and I'll change this to Python. So I just really like the minimax algorithm, although it's like less efficient. Like we don't have to train any data for starters because it's just unsupervised learning, and it just learns as it goes on. Oh, that's interesting. We've got C++23 here. So Python. Oh no, is there just Python normal? No, I think this should. I think there are a few breaking changes. Okay, so these are the 3 grids. I don't know why they. Yeah. Okay. Anyway, it would be helpful to know. So I assume it goes 1, like starting from the left, going to the right. 1, 2, 3. So I'm gonna go top left. So I'm gonna go 1. Okay. Now what I'm gonna do is I'm going to go 9. Okay. Now what I'm going to do is I'm gonna go 8. Then I'm gonna go 3. And I'm finally gonna go 4. And it's a draw. Yeah, literally you can never win against the AI. So for instance, I reckon when you just type in tic-tac-toe on Google, I think most probably it will use minimax. But I don't know how you would use minimax to be bad, because minimax by default, maybe you just instead you don't use any AI algorithm at all. You just pick a random one. Yeah. Okay. So yeah, so you can see this can be applied to games like 4x4. I saw an example earlier on today, which is like in an MIT Maker portfolio. Then there's also 4x4. There's chess. There's Go, and there must be lots of different games. Okay, so I'm just gonna go through this code again. So if the AI's move, so best move board. So this passes in. If we're not trying to maximizing, we're going to trying to minimize the human's score. So we're going to do board equals X, minimax. So we're just trying to minimize the score. And then if it's maximizing, we're going to try. Wait, when does it ever get to? Oh yeah, we're going to set to true. When it's the human score. So yeah, that's all for today's video. So first of all, what we do is we would minimize, because we're trying to minimize the human score, because we're passing in false. So first, we minimize the score, but then we maximize it, minimize it, and maximize it, and we keep recursively doing that until there are no further possible, because we only didn't range to 9. Okay, so then we do score equals minimax true. So we're trying to now, the humans go. We're trying to, let's see. We're trying to minimize. Oh no, so so what we do now is trying to maximize our score, because the human has just moved. But first off, what we would have done is minimize the human score. So yeah, you can see it goes like this, and then it gets into a recursive manner. So yeah, let's see what it says after this. So yeah, that's all. The minimax algorithm recursively evaluates all possible moves to find the best one. Its science score is based on the game outcomes. 10 for AI, -10 for AI loss. 0 for draw. The algorithm assumes both the AI and the human minimizer play optimally. I'm just going to play again and purposely do not maximize the value, because it says it assumes it, but it will still work for any. I think it will work for if the human's just making bad moves as well. So I'm just going to do. Sorry, I was in a bad move. So you can see it's still making the optimal route. So if I go 9, it's going to win. Yeah. So it doesn't need the human to play optimally for it to win, because it can still win. Like in chess, if a human doesn't play optimally, it is still easily beaten. And it's more easily beaten than if it plays optimally. Get what I mean? So yeah, that's all for today's videos. Thank you for watching, and I'll see you in the next video. Goodbye.